Welcome to our final year project presentation, titled A Multivariate Approach for Dengue Outbreak Prediction Using Machine Learning. Dengue continues to pose a serious public health threat globally, with rising case counts and death tolls. Traditional vector control methods are no longer sufficient. Our project explores how machine learning can be leveraged to enhance dengue outbreak prediction. The main questions we aim to address include: first, how can we accurately forecast dengue outbreaks using machine learning? Second, what climate factors most influence dengue transmission? Third, how can we build a user-friendly system for public health decision-makers? There are three main challenges motivating this work. First, traditional outbreak prediction methods lack both accuracy and timeliness. Second, vaccines are still limited, so most efforts focus on mosquito control. Finally, with the growing number of cases, there's an urgent need for advanced prediction tools. Our integrated approach, which combines climate and epidemiologic data, aims to overcome these limitations. Our project had four primary objectives. First, to collect and pre-process accurate historical data on dengue and climate. Second, to identify the key variables that influence transmission. Third, to develop machine learning models to predict outbreaks. And finally, to design a user-friendly tool that public health officials can use for real-time monitoring and prediction. Our methodology involved four key phases. First, data collection. Second, feature engineering. Third, model development. Finally, evaluation and validation. Each phase played a critical role in ensuring our prediction framework was robust and reliable. We experimented with a range of machine learning models, including long short-term memory, light gradient boosting, extreme gradient boosting, support vector regression, random forest, cat boost, and time series. By using a diverse set of models, we aim to identify which approaches best captured dengue outbreak patterns. Moving on to model performance comparison, extreme gradient boosting achieved the best results with an R-squared value of 0.926 and a root mean squared error of 10.38. Other strong performers included light gradient boosting machine and cat boost. Long short-term memory showed significant deviation from the actual values and had noticeably higher error margins. To improve predictive accuracy, we implemented an ensemble model using a stacking approach. The base models included extreme gradient boosting, light gradient boosting, random forest, support vector regression, and cat boost. For meta-models, we tested linear regression, ridge, lasso, and gradient boosting. We trained 2019 to 2021 and held out 2022 for evaluation. Among the meta-models, ridge regression slightly outperformed the others, achieving the lowest mean absolute error and root mean squared error. It consistently produced better predictions compared to models, making it a strong candidate for real-world deployment. We also create outbreak prediction model as well. To make the predictions more actionable, we categorized outbreak severity levels into three classes. From 0 to 100 cases is classified as no outbreak. Between 100 and 300 cases is considered moderate, and anything over 300 cases is categorized as severe. Light gradient boosting, it has correctly identified 5 severe outbreaks and 31 moderate outbreaks correctly. We evaluated the classification performance of both models. Extreme gradient boosting and light gradient boosting machine model. Extreme gradient boosting demonstrated excellent results, achieving perfect precision and recall for no outbreaks, and strong performance for both moderate and severe outbreak classes. It correctly identified nearly all severe cases, showing high reliability in critical scenarios. Moving on to our key findings, extreme gradient boosting was the best performing individual model, delivering the highest overall accuracy. Both extreme gradient boosting and light gradient boosting machine provided stable and consistent predictions across multiple years. We also found that lagged climate variables, such as precipitation from 3 to 4 weeks earlier, were among the most predictive features for outbreak forecasting. Finally, our ensemble model was the most effective at capturing outbreak peaks, making it highly suitable for real-world public health applications. In conclusion, we successfully developed an ensemble-based machine learning framework for dengue outbreak prediction. Extreme gradient boosting emerged as the best single model, and our ensemble approach ensured consistent results. We also developed a practical dashboard that can serve as an early warning system for public health officials. Our approach effectively captures climate disease dynamics through the use of lagged variables. Thank you. The video showcases a web-based dashboard designed to predict dengue outbreaks. The dashboard is divided into 4 main sections: cases, weather comparison, predictions, and bulk predictions. In the cases section, a line graph displays the number of dengue cases per epidemiological week from 2012 to 2022. Below this, a map of Rio de Janeiro state shows the distribution of cases. with a color-coded legend indicating the number of cases, from less than 1 to over 100. When clicking the map state, for example, Angra dos Reis, we can compare actual versus predicted cases for 2021 and 2022. The weather comparison section provides a similar map and graphs, but this time, it compares the number of dengue cases with various weather parameters. For Rio de Janeiro in 2022, it shows cases versus average precipitation, cases versus minimum temperature, and cases versus maximum humidity. By clicking the map, we can analyze the weather patterns in each city. The prediction section features a dengue outbreak predictor. Under the General Prediction tab, users can input various data points, including this week's and last week's dengue cases, average temperature, population, precipitation, vegetation, index, week number, and average humidity to get a forecast for the next 2 weeks. This section also allows for state-specific predictions. In the video, the user navigates to the Rio State-Specific tab, selects the city of Belford Roxo from a drop-down list, and clicks Predict to receive a forecast tailored to that specific location. Finally, the Bulk Predictions section allows users to upload a CSV file with dengue data for multiple cities in Rio State. The tool then processes this data and displays a map with the predicted dengue cases for a specific week. By clicking respective region, we can get the future predictions. This feature enables large-scale predictions for the entire state.